Bismillahirrahmanirrahim. Welcome back. So now I'm going to discuss the remaining part of this topic. So in the previous lecture, we discussed about the inorganic and partially inorganic, and this is the third part of the lecture. And now in this particular lecture or video, we'll talk about the organic polymer. So, organic polymers basically again the polymer that have in the skeletal they must have carbon atom in the backbone. So these are organic polymer, and for example, this is the example of cellulose, and then this one. After that, we have organic polymer grouping. Again, you have a natural polymer, so the polymer that's obtained from the natural source directly from nature, and also the synthetic polymer that is obtained from the fossil fuel like such as coal, natural gas, and petroleum. So, amongst the natural polymers, the importance are rubber, cellulose, starch, protein, nucleic acid. Okay, so I ask you one of the group in I give this nucleic acid writing a essay. So this topic will be covered by that essay, and now this one you have to write one paragraph for each student will write one paragraph about it, including the source, structure, and possible uses, and some other aspects which are also mentioned, which I am going to cover here. Okay, now and for the synthetic polymer, these are all the example of the synthetic polymer, and some of them I have already discussed, and some you're going to see now or in some other later on in some other lectures. Um, so these are important synthetic polymer which is produced in the company in the factory or in the in lab or in factory or in industry. Okay, now look at here, classification of the synthetic polymer classified by these three different ways, and we have already discussed them previously. Commodity or engineering polymers, thermoplastic, thermosetting, chain growth, and step growth polymers, so which is already discussed. So this is the same thing again. About the mechanism of the condensation polymer, I have already discussed this in the class, and you should know any mechanism for any condensation process could be asked, and you should know how the arrow pushing can be shown. Okay, and the chain growth, this is I have already discussed in the class, all the steps, and you must know. So we have discussed this before the first exam, but it is continue for the second exam and the final exam. So mechanism is always continue throughout the course. Okay, now move to the first one. Little information about the rubbers. So I pick some important point from the book. I cut and paste here. So at least you should try to understand from here and then read the handout which I give it to you. Okay, so where this rubber terminology comes from, that explains here. So the people long time ago, Mayans, who lives in the Western Hemisphere, they use this material before the Columbus introduced this into Europe, and they call this material as caoutchouc, and caoutchouc means weeping tree. And weeping tree, and the people still, some of the people in the world, they are still use this terminology. But the Joseph Parsley was the one who used the term rubber for the first time, because when he noticed that this caustic material can rub the pencil mark, so he gave the name as a rubber. So you know this structure? I have studied in lecture 2. This is isoprene, and isoprene is the monomer which is a diene, and after the diene you get this structure. This is called polyisoprene, and the polyisoprene, depending upon the double bond, so this is, we know this is 1,4 polyisoprene. So if you forgot, go back in the lectures where I mentioned what is diene and how isoprene polymerize and give 1,2 or 1,4 microstructure. So the 1,4, this is because at position number 1 the chain is continue, and at position number 4 chain is continue. That is why it is called 1,4. This is isoprene and this is the double bond. But if the double bond given to you in three-dimensional form, then you can also see and make a decision if it is cis or trans. And this cis and trans is really very important to understand, because this play a very important role. So this is you can see here. So if the three-dimensional structure is given, or then you can see. Otherwise, from here you can just say 1,4 polyisoprene. So now these are the different rubber material. All these are the names, and you should know the difference between each. So this Hiva and this is Guatapercha, and that's have the difference. Here is cis 1,4 microstructure, here is trans 1,4 microstructure. So if the question asks what is the difference between this and this, so you should be able to answer that this is cis 1,4 and this is trans 1,4. And if it is asked support your answer with the help of the microstructure, then you should be able to write cis structure of the 1,4 and trans structure of the 1,4 of isoprene. These are other material and these are their potential uses. So look at here, this is the latex gloves. Nowadays the latex gloves are made by using this material. Okay, but before that it used to have, people use this Hiva material to make gloves, but they have actually stop making these material. So why they stop making these material and using these material to make latex gloves, this is the question. I leave it for you to read. So you have to read from the book and find out why latex gloves now they are making using this material, not this material. What is the reason behind it to stop the use of Hiva for making the latex gloves? Okay, that's a question for you. When you read the handout of the book, you would know what is the reason behind it. I may ask this question. Okay, now amongst the polysaccharide, the two important polysaccharide we're going to study is cellulose and starch in more detail. Okay, this will be discussed in more detail, cellulose and starch. So as the name says, the cellulose come from the nature, which is a plant source, and the structure is given to you here. This is a glucose structure, the cyclic 6-member cyclic ring. You should all know how the glucose structure, right? So I'm not talking about how this glucose structure, right? And this is, but just to remind you, this is carbon number 1, this is 2, 3, this is 4, this is 5, and it's a 6-member ring through the help of oxygen. This is carbon 1 and this is carbon 4. So the chain formation, polymer chain start growing from carbon number 1 and different second monomer carbon number 4, that is the one here. So if I ask you to show how the dimer form, you have to write another glucose unit here and connect this line with the carbon number 4, which is this one on this side, and then one of the second monomer to the third one, and so on. So that's the way it could be asked. As I always mention to you, I could ask you to show you how dimer, trimer, tetramer or polymer chain sequence look like. So you should be able to draw this one. And what is this cellulose? So now in the glucose 6-member ring structure, you know this is an axial position and this is equatorial position. Axial, equatorial, axial, equatorial. So you should know this one. So in the cellulose, when the carbon 1 of one monomer unit and carbon 4 of the other monomer unit, a dimer form. That is why it is called 1,4 linkage. This is called 1,4 linkage. And when the oxygen is at the equatorial position, then it is called beta linkage. And when the oxygen is at the axial position and connect, then it's called alpha 1,4 linkage, and that's a starch. So this is the basic difference between cellulose and starch. This is 1,4 beta linkage, and if the O is here and H is here and the bond formed from the fourth position, from the beta position at carbon number 1 to the fourth carbon of the other monomer unit, then the linkage will be named as alpha 1,4 linkage, and that will be named, that compound will be starch. So that is the only difference between, the major difference between starch and cellulose. So when I'm going to discuss about the starch, then you will know. So this bara 1,4 linkage is very difficult to break. That's why this is not cellulose. People don't eat. The human being and other animal, they don't eat this one. Sorry, the human being, they don't eat it because we don't have enzyme to hydrolyze this linkage. Okay, otherwise we can eat this one. But now this that's it from here. And what this highlighted thing is saying that except the hydrogen, all other substituents are at the equatorial position. So other substituent right now is OH. So OH and this group CH2OH, they are all at equatorial position. Okay, so this is the way you should remember. But for your job is just to remember the structure, how the cellulose look like, and how it is connected, one monomer unit connected to the other monomer unit. That is really important for you. What is this linkage is called? Alpha 1,4 or alpha beta 1,4. Okay, and that's an important thing to remember here. Now look at here, we have three OH group left in the polymer. One OH here, one OH here, and one OH here. So later on in the lecture, I will show you the modification of the cellulose, or you can also say the derivative of cellulose, how different products can generate from cellulose. So the reaction will take place at this position, and this position, depend upon the molar ratio of the reagent which we are going to use. If you use 1:1 ratio, then only one of the three OH will react. If you use 1:2, then two of them. And if you just use 1:3, then all of them should be should be used. So when we talk about this later on about the reaction of the cellulose, then you don't need to write all the time this structure, because that takes too much time. So what you have to do, you just take this one and then equate it as cellulose, which I will show you later on, cellulose dash OH. So then we know that we are reusing the cellulose, and at the position of OH you want to show the reaction, which you will see later on. But you have to show this one, that this is the cellulose and it has bara 1,4 linkage, which is equivalent to cell CELL dash OH. And then use this formula and you can show the reaction to save the time. Okay, so this is the way. Of course, I am teaching you in case if the university open and I take the exam in the class, then this type of questions will be given to you. Okay, so now this is the informations about the polysaccharide cellulose. You read it, but important point I highlighted here, the cellulose which you get from the plant is called the native cellulose. Okay, and this native cellulose is different than the regenerated cellulose. So we should know the difference between native cellulose and regenerated cellulose. So if you understand what is regenerated means, then you will automatically know what is native cellulose. So the cellulose which you obtain and don't make any change, then it's a native cellulose. And native cellulose is highly crystalline. Okay, and it's a linear, highly crystalline, and it has a very high degree of intramolecular and intermolecular hydrogen bonding. So if you look into the structure here, you know this is the OH, and this O can make a bond with this H. So this is the molecular hydrogen bonding, and then you have a one chain and you have another chain, and this OH can make a hydrogen bond with the other H of the other chain, then it's an intermolecular. So that's why both type of hydrogen bonding present. That's why it says intramolecular and intermolecular hydrogen bonding. Okay, that's why cellulose cannot be is not considered as thermoplastic, because this hydrogen bonding make it like a cross link, and that is why it's actually decomposed before it's going for melting. So it's kind of a thermoset. Okay, but not really a physical cross linking, but because of the hydrogen bonding it behaves like that. Okay, now because of this, if you look here, you will say that you have OH here, OH here, so it's like an alcohol. So it should be soluble, like when you dissolve alcohol in water. So because of the polar bond in water and polar bond here, so like dissolve, like it should be dissolved. But here you notice that the most of the like the cellulose is not soluble in water. It's insoluble. Reason is because of this hydrogen bonding, intramolecular and intramolecular hydrogen bonding. It does not allow it to soluble. But there are some solvent in which it can surrender and get soluble, and mostly this copper 2 ammonia compound, which is also called Schweitzer reagent, and copper 2 diamine. These are the solvent which we can use to dissolve cellulose. And we can also use some other solvent. The names are mentioned here. Nowadays they are used to to dissolve the cellulose. But once you use the cellulose and dissolve in alkali like sodium hydroxide, then instead of dissolving it just swell. Okay, and that is the process. When it is undergo swelling, then the from there a regenerated cellulose can be produced. So what is the difference between this and this? It's kind of a you have a cellulose which you dissolve into a solvent or it swell, and after several time, and it start degrading. Some of the chain detach, some of the chain break, so molecular weight is actually decrease, and after that you wash out and recollect the cellulose from that solution. So this, because it is regenerated, that is why it is called regenerated cellulose, which is more less crystalline compared to the native cellulose, and they have some other property, and that is why it is used mostly in the industry for its special application. Okay, so that's what the so here the cellulose swell in water if you put it in water or in base. Okay, so the base solvent polymer known as alkali cellulose. So you have cellulose and you put into sodium hydroxide and potassium hydroxide, then the cellulose after the swelling, what it's called is called alkali cellulose or soda cellulose. Okay, so we leave it for certain period of time and then wash it out, and then this cellulose is called it is used for regenerate is used to prepare the regenerated cellulose. So when you want to prepare a regenerated cellulose, first you have to take the cellulose and dissolve in alkali, sodium hydroxide or potassium hydroxide, then some other step, then you get the regenerated cellulose. But before that regenerated cellulose, if you have this alkali dissolved cellulose, okay, and then you wash this alkali, then this process is called mercerization. Okay, this process is called mercerization. And what is this mercerization? Because of this, so mercerization is the process is what this process is treating cellulose, for example cotton, into base, and then you wash the base. That's a simple process. You take the cellulose, for example cotton, you put in the sodium hydroxide for a certain period of time, and then you wash. Okay, and then this process is called mercerization. And what is the advantage of this mercerization? That after this process this cotton has a high luster, means shine. So sometimes you see the cotton clothes look very shiny, and that's the reason of the shine. Okay, and compared to the natural cotton, it's also less dense, so it's a little bit like less heavy, and also it has less crystalline, so it is softer in feeling, in touch feeling, and that's why they have improved dyeability, so you can give different types of color very easily. Okay, so that's why this is the, so mercerization here is also very important terminology to remember. What is mercerization and what you achieve from this mercerization? Okay, now let's talk about the regenerated cellulose. So how to regenerated cellulose prepared? Okay, so regenerated cellulose, here in few slides I will teach you about how regenerated cellulose can be produced. Okay, as we mentioned that the regenerated cellulose is different from the native cellulose because extensive degradations takes place during the process of dissolution. Means we take this cellulose and you put into the alkali and some other chemicals, and after that you leave it for age, like for some period of time, and during that process the chain will start to break and cleavage takes place. That is why it is called extensive degradation. So after the process finish and you recovered the cellulose, that is why it is called regenerated cellulose. Its molecular mass is less than the molecular mass of the cellulose which you use as a native cellulose, and also some other property like the crystallinity become less. Okay, how do you do this one? So the process of making that regenerated cellulose is called xanthate process. Xanthate process or viscose process. Why it is called viscose process or xanthate process? So this is called xanthate process or viscose process, because when you put the cellulose in alkali, okay, then you get a very viscous liquid, and that is why it is also called a viscose process. And then you leave it for certain period of time, and that depends from different to different product, and then the molecular weight is reduced, drastically reduced. Okay, what is the role of the alkali which we use here? Nobody knows with certainty still. And in this slide it shows that how you do this one. So you take the cellulose. See, this is the one I was talking about. Instead of writing the complete repeating unit structure, you write that CELL-OH. Okay, instead of writing this structure, you just write here arrow or three equal signs, dash dash dash, and then you write CELL-OH, and then it means that you are trying to show what is happening here. And then here you take this one and put in sodium hydroxide, and also you put it carbon disulfide. Okay, and then the product which is obtained from here is called xanthate, or say viscose. That is why this process, this is xanthate, and the process xanthate or viscose, that is why this process is called xanthate process or viscose process. So how this reactions takes place? Okay, so carbon disulfide, carbon has two valency like carbon dioxide. So O double bond C double bond O, that's a carbon dioxide. Similarly, this CS2 have the structure. So you have S double bond C, then double bond C. Okay, so what happened now when you react with the OH? So what the OH does, first the OH react with NaOH to make an alkoxide ion. What alkoxide ion we have discussed in the previous chapter, like RONA. So let's say this is R, so this is O. So the H will go with water here, so leaving the negative charge here, and N will balance this negative charge like an alkoxide ion, which is a strong nucleophile. And this nucleophile will come and attack here. So one of the C double bond S will break. So look at here, this O is attacking onto the carbon. Okay, so here is a double bond, here is a double bond. So one of the double bond breaks. That's how this O got connected with the C. The other double bond break in favor of S, because S is more electronegative than C. So S will leave with the negative charge, and this will be balanced with the sodium positive charge. And of course this water is produced, which I already showed. So this is called xanthate or viscose. Okay, because of the free elemental sulfur, we get some very pungent odor, unpleasant odor, because of this volatile sulfur byproduct which is produced in this reaction. And after the formation of this product 8, we leave this for certain period of time, that's called aging. And during that process, actually some of the chain will break, and due to that molecular weight and decreases, and crystallinity of the native cellulose decreases. After this process is done, then we have to find the polymer back. So what is the, how do you get the polymer back, this or cellulose back? This is mentioned here. What you have to do, you take this your xanthate, and you put this one into acidic solution. So basically you are doing the hydrolysis under acidic condition. So what is this acid will do, it will come here and make the cellulose ClOH and break this molecule. So this double bond will form again, so you will get carbon disulfide recovered, and you get the sodium ion, free sodium ion, which will be balanced by the with the negative ion which is generated from the acid. For example, if you use the acid HCl, so the Cl will be reacting with Na to make NaCl, or if you have SO4, H2SO4, then the SO4 will balance with sodium. Okay, and the regenerated cellulose which is obtained this way can also be produced by using this chemical. Okay, then the process is called copper ammonium process, and also saponifying cellulose acetate can be used. Okay, these are other methods, but most important is the xanthate process. Okay, and that's why, and the product which is obtained by this method is called viscose rayon. The name of the product, the regenerated cellulose, is called viscose rayon, and it is a very useful product for textile industry. So that's what you have to especially remember. Now some reaction of the cellulose or derivative formation of cellulose. So cellulose can be changed into cellulose ester, cellulose ether, or you can do the grafting by introducing a different polymer on the cellulose. And why we do grafting? Because we want to introduce some different property into cellulose, and also a cross-linking. All four reactions are important in cellulose, and these four reactions you have to study as well in starch. So here concentrate on cellulose, and the similar reaction you can do in starch, because the structure is pretty much same, so reaction will be almost the same. Okay, the first reaction is ether formation, right? So now you have cellulose. You remember, I told you what is cellulose. You use this structure, but you have to show if it is asked in the exam one time, and then you can continue with this one. So you know in cellulose we have 3 OH remaining left. Over there the reactions can be takes place. So the first product, cellulose ester, is cellulose nitrate. How you do this reaction? You put nitric acid. So the nitric acid, this HO, OH will take the H from here, make the water, and NO2 will attach with this. Basically this will become NO3. Okay, so that is called cellulose nitrate. So when all the OH is replaced by NO2, this becomes cellulose nitrate, all three. And this is the gunpowder, the first gunpowder which is made in long time ago. Only when all three OH is replaced by NO2, so that become a gunpowder, cellulose nitrate. Okay, so you should be able to show how this reactions takes place if it is asked to show and show. Then this is the way you have to mention all three, or just simple one this way, and balance the equation. Okay, not necessarily required to balance equation, but usually it takes when you do the reaction which HNO3, all three OH will basically react depending upon the what ratio you are using. Okay, now that is the acetate reaction. Again, you have acetic anhydride and you have alcohol. So you have seen this reaction so many times. I discussed this reaction in N group analysis, how to do the reaction with OH, if you remember. So N group analysis, the OH reacted with acetic anhydride. So one acetoxy group will react will come and attach here. The H will go the other part, and acetic acid will release. So this is the way you can produce cellulose acetate. Remember, this reaction also takes place in all the three OH position, and this reaction takes place under acidic condition. Okay, and why we are doing all this reaction, and what is the important where these products are used, this is your job to read from the handout of the book I give you. Okay, now cellulose ether, next one. We want to show how the ether will be formed. These are the different like the reagents can be used. I will concentrate only on the cellulose ether, how to form. So look at here. This is your cellulose, and this is the sodium hydroxide. So what the sodium hydroxide do here? Sodium hydroxide does here, I already mentioned to you in case of the xanthate process. So this will generate an alkoxide ion, which is a strong nucleophile, creating a negative charge here. The H will go with OH. This negative ion will attack here on R and kick the Cl out. Nucleophilic substitution reactions. The O will attack here and kick the Cl out, and that's how you get the ether linkage. So carbon here, oxygen, and then carbon. So this is the ether, and that's how ether you get. Okay, now what kind of ether you can get? These are the different reagent you can use. Here are, if you are, R can be CH3, so then you get methyl ether. Okay, you can, R can be ethyl group, so ethyl substituted group you can get. And these are different R group. Look at here, R here. So where I should attach this one, if I want to change here, so it's from CH2, this Cl should be here, CH2, not at OH, because this is the one we need. So when this O will come, and O will attack here and kick the Cl out, and this will become the part. So all these reagents you should practice in your home how to do reaction. I could ask any of them in assignment, that how to do this reaction. Now the next way of making the ether substitution is this one, the cellulose you have, and you can use this epoxide, and then this OH can attack here or here depending upon which one is less substituted, and then the ring will be opened. So look at here, because this is the same here, so this O will attack here, the bond will be open, and this O negative will take the H from here, and that's how you get this product. Okay, and the methyl cellulose, if you have a methyl group here, then if you suppose if you have ethyl cellulose, if you have an ethyl group here, is most widely used for plastic application because it's not very soluble. But methyl cellulose is water soluble. So if you use methyl group here, you get a methyl cellulose which is water soluble, and it is used for food thickening, like making ice cream or some other stuff in which you mix this one. Food thickener can be used. Now, uh, next is the graft copolymer. So how do you do the grafting? Okay, so there are different ways of doing the grafting. One of the important method. And why grafting you want to do? You want to change the property of the cellulose. Is a polymer which we introduce a different polymer, or sometime we introduce a monomer and start growing the chain from there, and due to that property is changed. That's how you do. This is one of the method of doing the cellulose grafting, is by taking the cellulose and we introduce the cobalt 60 X-rays to create the reacting center, and then from this reacting center we can introduce any monomer to put a new polymer chain. But look at this one. The most important one are the two, means vinyl or non-vinyl grafting. How to do vinyl grafting and non-vinyl grafting? One of the important is using, first you take the cellulose. Cellulose is see this OH. Remember, all the time the reactions takes place at the OH position. So this first you react with this a chain transfer group. So the cellulose react with the chain transfer group, like for example mercaptan. So the OH of the mercaptans will remove, and this will be connected. Now this cellulose is ready for any free radical polymerization. Now this is ready. So this SH bond can be break to create a free radical here at sulfur, a free radical on H. Okay, homolysis you have learned. So you use a peroxide initiator which create a free radical here. That is the initiation at sulfur. Free radical will be generated. So S dash H bond will break, one free radical on S, other free radical on H. Okay, so this S free radical will attack here to attach with the CH2, and this bond will break in favor of the CH, creating a free radical here, and then this will combine with the second monomer and the chain start to grow. So look at here now, the cellulose O, so the O CH2 CH2 SH, so the H is gone, so the S is attached to CH2. That is why after the S you see CH2. After CH2 you have CHR, so free radical here. The same chain growth polymerization technique which we have learned before. Okay, same mechanism, everything. So the mechanism, unfortunately we don't have the class now, otherwise this is also a very good question for mechanism. But if the university open and the exams takes place in the class, then it could be asked. So this one, and then the second monomer and third monomer, and that's how the chain continue to grow. So this is the cellulose, and then this is the different polymer. So based on this polymer, what monomer you use, the property of the cellulose can be changed. Okay, so this can be any monomer like propylene or styrene or anything. That's why I wrote it here R. So any vinyl monomer can be given here and ask you to complete the reaction and show the mechanism on all three steps: initiation, propagation, and termination, and the same way as we discussed before. Okay, so this is the vinylic grafting, and this is the non-vinylic grafting. So you have cellulose and you can use an epoxide like this, and then again this reaction we have discussed before. So this will attack here and this O will be free, and then this O will be a negative charge. This will attack on the second epoxide ring, and that's how the chain will start to grow. Look at here, I will show you first one. So this oxygen will attack here. So look at here, this is cellulose, oxygen, and this is attached to CH2. Yes, this is CH2, and then CH2, and then OH, this OH. Okay, but now we want to show the chain and continue. That's why we are writing here N-1, and we are showing one more unit outside. Now this will attack to another, this one, this monomer, and then that's how the chain will continue to grow. And this what is this the monomer you introduce, the property of this monomer will change the property of the cellulose or modify the property of the cellulose, and this product is called ethylose. Okay, and the product which is produced by this reaction marketed with the name of ethylose. Okay, this is grafting. And the last one is the cross linking. So we already know what is the cross linking. When one polymer chain, other polymer chain are connected from the different position, that's a cross linking. And why do you do the cross linking? Because we want to increase the mechanical strength of that product. So one of the important use of cross linking of the cellulose is the impact crease resistance. So before, when this technique was developed, when people use the cotton clothes, after one time or after one few sitting, it's really wrinkles all where is a wrinkle, it's not, doesn't look good. So now after this technique we have crease resistance product or durable product. That is why this is nowadays a major industry. Okay, so how you achieve this one? Of course, you have cellulose. Remember, this is the modification. You are not making the polymer. Polymer is already there. You are just making some changes, which is called modification or derivatization, introducing some other property. So you need to do the cross linking. You have learned in the inorganic polymer when I taught you in the previous lecture about how to create cross linking. So for cross-linking, you need a cross-linking precursor, the molecule that help in doing the cross-linking. So the cross-linking precursor which are used, important one are these one, number 10, 11, 12, 13, and these are the all cross-linker, and which the picture can be shown here. This is number 10. See, this is the cross-linker, number 11, number 12, number 13. You don't need to memorize these cross-linker. If this question is given, this cross-linker is given to you. You just have to show how the polymer chain connect with each other. So it's very simple. Look at here, this one OH here and one OH here. So if you want to show a cross-linking reaction here, you have to show two cellulose chain. So one of the cellulose chain will connect here, another chain will connect on this side, and that's how these two chain are connected with the help of this material, and that's called cross-linking. Same will be here, same will be here. In this case, from this OH here you have two of these, so this reaction will take place at this OH and this OH, and that is the cross-linking. And one of the reaction with the 10 with the 10 is shown in the slide. So look at here, this is the 10, and this is one cellulose chain OH, this is another cellulose chain. If you show only one chain and write this product, this is not considered correct. So remember that whenever you show the cross-linking reaction, you have to take two chain at least and connect with the cross-linking agent. So you put the cross-linking agent, this one here, so one OH will react with this to make connect here, and the other one from this side, and that's the cross-linking product. Okay, so that's how this cross-linking takes place. Other cross-linking agents are these are the other cross-linking agent that can also be used. So you can read about this, how this will be utilized. Okay, and the main purpose is just to create a cross-linking. Okay, now starch. So cellulose and starch are pretty much identical, but the difference is that they have alpha 1,4 linkage, not beta 1,4 linkage. So now if you see the structure of the cellulose, look at here. In cellulose, the structure start from the equatorial position. The O was at the equatorial position, so that's why it is called beta 1,4 linkage. But now O is at the axial position, that is why it is called alpha 1,4 linkage. Otherwise everything is same. And but one more difference is here at this position number 1, 2, 3, 4, 5 and 6, carbon number 6. At carbon number 6, this OH can give a branch, and that is these are the two difference between starch and cellulose. Okay, that is why most of the derivatization or reaction of the cellulose is same, starch is same as cellulose. So now get back to this main information about the starch. So you have 1,4 alpha linkage rather than beta linkage. Okay, and branching may also be occurred. So if you break the polymer chain, you will get D-glucose as a monomer. Okay, because this is the monomer which is combined. And all these informations, basically when you get this starch from the nature, this is composed of two types of polysaccharide, amylose and amylopectin. Amylose is a linear polymer without the branches. Amylopectin have the branches from the carbon number 6, and this is their range of the molecular weight. So if you don't have any branch, this is amylose. If you have a branch, then it's amylopectin. But starch is basically the mixture of both. Okay. So now all these you can read here, and this is the picture. For example, this is from here you start. This is the starch molecule, and then this is the carbon number 6, and here one more D-glucose unit is connected, which is also connected to the next one, and that's how the chain start to grow, and that is why it is called amylopectin. Okay, because they have so much branching, that is why highly branched structure and permeability, that is why starch is not suitable for plastic or fiber application because of this branching and permeability. Because of that, this is not very good suitable for plastic or fiber application compared to cellulose. Okay, now if you look into this one, I wrote it here, just read all this information. All the reaction of the starch are same as in cellulose mentioned in the previous slide. Change the starting material as a starch and rewrite all the reaction. All those reactions which we have discussed in cellulose will be same here as a starch. So one time you have to write the actual formula, and then you can write STAR-OH and then show the reaction. Okay, so that's about so some other important polysaccharides are three important. One is chitin, and the other is chitin is also called chitin. Some people call it chitin, and the other is called chitosin or chitosin. Okay, so whatever you like call, you can call chitin or chitosin. These are the one of the important polysaccharide, and the other is algic acid. So where you get this one, you can read here, but I will show you only the difference in the structures, which you more important to remember, so then you know how to show the reaction. So look at here, this is like a cellulose structure. Look at the position, beta 1,4 linkage. So in catin, chitin or chitin, it's a beta 1,4 linkage, not alpha 1,4 linkage. It's a beta 1,4 linkage, and all the structure is same as like cellulose. But look at the carbon number 2. Carbon number 2, you have this NH2 group, which is protected with the acetylated group. So this is acetylated amino group, position number 2. Look at here, in this case is same mentioned here. It is protected chitins have the acetylated group. On the other hand, your chitosin has NH2 group. This is the only difference. Okay, this is the only two difference. Okay, now look at here, this is the acetylated group that is used to protect the NH2 group. If you cut this part and bring the NH2 back, then it is called chitosin. That is the difference, remember. So if the question asks, show the question with chitin or chitosin, then you make the change in the structure and show the reaction. So if it is protected, then reaction will take place only from these two positions. If it is not protected, then all three can be involved in different reaction. Okay, and one of the important application of this chitin and chitosin is their application in sorry in um, in the food industry, cosmetic industry, and wastewater treatment. The food industry, cosmetic industry, because of their gel formation property, because they can make a gel, that is why they are used in food and cosmetic industry. Also in the wastewater treatment. Why? Because you see here the structure, they have and have the lone pair here, because this nitrogen with the lone pair can make a chelate with the heavy metal. So if you want to remove the heavy metal from the wastewater, this material can be used. And also this can also help in flocculating the protein. So if you have a waste protein in the seawater and in the wastewater, and you want to purify it, then you can remove metals and all other things, but protein is very difficult. So the chitosan is used, so it will make a flocculate, like a precipitate it out very easily. Okay, this is the one of the important applications. So remember the structure, changes in the structure and how the reactions takes place if it is given to you, and important application. So I mentioned to you about chitin and chitosan. The last one is alginic acid. So alginic acid is obtained from the alga or algae, from the sea. Usually at the seashore we got the plant, and from there you get it. How the structure look like? It's very simple. At carbon number 5 you will see a change. 1 2 3 4 5. Here you have a carboxylic group. That is why it's called alginic acid. All other structure is similar to cellulose. Beta 1,4 linkage. So if it is asked what is the basic difference with beta 1,4 linkage and you have carboxylic group at carbon number 5. Okay, so that is the alginic acid. So that's about the polysaccharide. The last one is protein. Okay, so the protein are the basic building block of animals and are therefore the primary interest to biochemist, not for polymer chemist. So you have to just study a little bit about it, because one of the synthetic process is very important, which is developed by the polymer chemist, but nowadays it's used by biochemists. That's why in polymer chemistry we have to study, otherwise there is no direct relation I can see here. Okay, yes, from the synthetic point of view it is still important. They are the major constituent of skin, nerve tissues, and blah blah blah, so many things you can read here. Okay, this is the major field of the biochemistry, but we shall discuss only the some basic principle point, that protein structure and synthesis. So protein, and the proteins are also called polyamide, so which means that the monomer unit which are joining together, they are joined together by the amide linkage, and amide linkage you have studied before. Okay, so the basic monomer which is used for making the protein is alpha amino acid. If you forgot what is alpha amino acid, go back and find out the structure. Google and find out how the structures look like. Alpha amino acids. Okay, or I will show you one structure here as well. And this is the monomer unit. So both the carboxylic group and amino group are present at the alpha carbon. So that's why this carboxylic group and amino group can connect together to make an amide linkage. Okay, these are alpha amino acid. So there are different terminologies the people use. So because of this amide linkage, people call it polyamide. Okay, but the protein chemists call it polypeptide, because the linkage, amino linkage, they call it peptide linkage. So once two amino acids combine together, they call it dipeptide. When three, then it's tripeptide and tetrapeptide and oligopeptide, and then polypeptide. But the polypeptide still have some discrepancy in the terminology. Some people says that if you have one around molecular weight around 10,000, then you call it polypeptide, and more than 10,000 is called protein. And something that fewer than 50 amino acid will be considered as polypeptide. So if 50 amino acids are connected with each other, less than 50, then it's polypeptide. Other than that is all protein. So these are the two different terminologies people use. So this is the amino acid. So if I just remove this bracket here, so you have C double bond, and here you have OH, and here you have NH2. So this is an alpha amino acid which have carboxylic group and NH2 group. So what happen if I write this amino acid and one more amino acid here? So the OH of this carboxylic group, the H from the NH2 will connect. That is why here I am writing H outside the bracket, and here OH outside the bracket. That is the continuation of the chain. So the basic repeating unit of protein will be written this way, and the amino acid is the building block. So as we know, the amino acids, all the amino acids which we in the human being, or sorry, in the mammals, or any mammals including human being, we have all the configuration is L shape, L type configuration. So there are two different configuration, L and D. So they have the L configuration, and also they are not existing in the acid, or they are existing in a dipolar ion form, means positive and negative ion both are present, and they are called Zwitter ion. Look at this structure here. This is the L formation of the amino acid, and because we have carboxylic group and NH2 group, so carboxylic group is acid which can lose H plus, and NH2 act as a base that can accept that H plus ion. So here we have NH3 plus. Okay, so this is called deuteriene, and this structure is pretty much similar to what they call it L-glyceraldehyde, because this structure is similar to L-glyceraldehyde. That's why the configuration here is also L. If you forgot what is L and D configuration, go back in organic chemistry and find out what are these. Okay, so this is the one. Now, as a polymer chemist, the important thing is just to show you how protein can be prepared. So one of the best method for the synthesis of protein is called Merrifield solid phase peptide synthesis. Peptide means peptide linkage. And this is very important method because before the development of this method in 19 something, the synthesis of the protein is very difficult. It required several steps one by one. So you connect one monomer with another monomer, and then you have to purify and remove all the unreacted material, which is really painful. But because sometime during the washing the chain get break, so now this solid state synthesis make the life easier, because all the time the monomer attach on the polymer support, and because the polymer is insoluble in solution, so washing is very easy. So when you wash, all the unreacted material or byproduct is very easily removed, and your polymer chain remain intact with the polymer, which later on with cross-link polymer, which later on remove. So because in here we use a cross-link polymer which is solid, that is why it is called solid phase peptide synthesis by the name Merrifield. That's why he got the Nobel Prize in 1984, because this is the fundamental breakthrough in the synthesis of protein. Okay, so how this reactions takes place? It's very simple. What he did, he used the cross-link polystyrene. So polystyrene, when it react with divinyl benzene, is cross-link polymer produced. I have discussed cross-link polymer beads in GPC. So the same product can be used, and this polymer can be used. So now if I show you the equation, then you will understand. Look at this equation here. Look at this. P is the polymer polystyrene. So just assume here you have a benzene ring. Here on benzene ring and para position you attach CH2Cl. Okay, just assume this is your benzene ring. So benzene ring para position you attach CH2Cl. Okay, but actually it is a cross-link polymer, so we are using a polymer, and this is solid. This is not soluble in any solvent. Okay, now this is the starting point, and then you take your monomer. Remember, in monomer you have a carboxylic group and NH2 group. So if this is NH2 group and carboxylic group are free, then they will start reacting with each other. Like this is the monomer, okay, like COOH group here and NH2 group here, and you take one more monomer like that, then the COOH from this monomer 1 can react with the H of the other monomer, and instead of reacting here, it will start reacting with each other. That is why we need the protection. So we need the protected amino acid, which amino acid you want to connect. So the protecting agent which we use is called Bock group, that will block the NH, so it cannot react by itself. Now this C carboxylic group can attack here and kick the Cl out, and that's how this first monomer connected to the cross-link polymer. And that's the product you have. Now you want to attach the second monomer, and that's how your chain start to grow. Okay, so now this is connected here, this is connected to the solid piece. So if you wash this one, then whatever the unreacted monomer, whatever the byproduct here, whatever the impurities here, can easily be removed without detaching this one. So the next step is, now you want to bring the second monomer here. If you want to bring the second monomer here, so you have in the monomer you have NH2 group and COOH group. So COOH group can react here at N position, which means that this need to be removed. So second step is the deprotection. For deprotection, second step, we use any acid under and with the acetic acid combination, and then this will break. So this Bock group will break. The Bock group will be decomposed into these byproduct, carbon dioxide and this product, and NH2. Now look at here, the amino group is free. Still it is attached to the polymer chain. After that, we are going to introduce the second monomer which we want to introduce. Of course, the second monomer should be initially protected by the Bock group. So now this is going to be introduced, and now when we are going to introduce here, we want to get an amide linkage. How amide linkage produced? This carboxylic group here will react with this H from here. So the OH from here and H from here will lose a water molecule, which is in the condensation process, water molecule will be loose, and this is called dehydration. In order to promote the dehydration, we use DCC. Okay, later on I will show you a little bit, but this is your job to find out how DCC work as a dehydrating agent. Now the second part is attached. After the second part attached, now look at here, this is the first, this is the second monomer. I put R1 and R2 just to distinguish, otherwise the same monomer can be used or a different monomer can be used, depend upon what you want to make. So now the second one is connected. Now the third step is just a repetition. What you have to cut this BOC, bring the NH2 here, and then introduce the third monomer and fourth monomer and fifth monomer, and that's how the chain start to grow. That is why we are showing this line here, the chain continuation. When you get the complete sequence, whatever the sequence you want, how many monomer unit you wanted to connect, 50, 60, 100,000, whatever. Once you reach to that many, then you have to remove the Bock group first to get the free NH2 group, and then you have to detach the chain from the solid polymer. So here you have to introduce HF. Okay, after the HF, in first you have to remove Bock. And how would you remove the Bock? This is the procedure. You put this group to change to bring to Bock. When the NH2 group regenerated, and then after that you introduce HF. So the HF will break the bond from here, from this position. You get your polymer, free polymer back, and this is your protein, and this is insoluble, so it can be easily separated from here, and that is called the uh, peptide synthesis, because this is the amide bond, which a polymer chemist called it amide, so polyamide, and protein chemist called it peptide bond, so this is a polypeptide, depending upon how many polypeptide means peptide linkage you have. It should be 50 or more, then it's less than 50, then it's peptide. Other than that, it will be protein. Okay, so that's the take place, and here is the summary how this reactions takes place. You can read first. A Bock protected amino acids attached to the insoluble polymer. Which polymer? Cross-linked polystyrene via an ester group. Look at this. This is the step I'm talking about. So this is connected to the insoluble polymer via an ester group. So see, this is an ester linkage. This is the first point. Second point, protective group is removed under the condition mild enough. Why the mild enough condition required for this deprotection? Here we want to remove this Bock group, so we need a mild condition. Why mild condition? Because we don't want this bond cleave, this bond break. So we want condition in which your ester linkage survive, but this bond can break, and this is the chemical is used to do this job. So after that, the second Bock protected amino acid is going to use. Of course, now the second amino group introduced, that it should be Bock protected. Look at here. This is the third one you introducing, and this is the Bock protected group, and that's how you get the second is introduced. Okay, but you need to use a strong dehydrating agent along with a strong dehydrating agent and DCC, because the water is generating. We need to generate water. If the water is still there, then the reaction will not take place. So you need a strong dehydrating agent. So what this dehydrating agent actually does, look at here. This is the structure of DCC. Okay, so when you add into the molecule here, when you add here, and this OH from here and H from here is removed, water molecule form. Where this water goes, look at the structure. Here, this is the DCC. The water will come here. One of the H will attach here. One of the H goes here. And the bond will be created here. And the O will go. And this is the product. So DCC will be converted into dicyclohexyl urea. So DCC will be converted into this product. And that's how water was consumed. And the reaction completed. Then you repeat step number 2 and 3, whatever the number of time you wanted. And finally, you separate the peptide or protein from the polymer support, and this is called solid phase peptide synthesis. And this is one of the important peptide synthesis technique, and this is always a choice of the questions for the exam. Thank you very much, and inshallah next week, or if I get the time soon, I will upload the lecture from the chapter 8. Have a wonderful day. Bye now.